get started here. Welcome to lecture number whatever it is about, and so we're still talking about so-called Tame's theory mixed with control theory. And what I want to talk about today basically are some issues with compact trajectories. And well, this path enclosure thing, which some of us are very familiar with, and some of us vector fields. I argued that we needed to make an assumption. First of all, we should be looking at things that don't define irrational power, their own minimal, don't define irrational powers. And there was another assumption that I argued for was that we should assume that at least all compact trajectories of linear vector fields are definable in the structure. And one of the reasons why we even have to assume this is because we don't know it's always true. We don't know that we do know that you can always add these, you can add all compact trajectories to linear vector fields and we'll stay on minimal. We don't know whether the field of exponents is preserved. The only thing we know for sure in that setting is that the resulting structure will be exponentially bounded. That's all we know for sure. But somehow the idea that you should be start off with a no minimal structure with the field of exponents Q, and then add, say, restricted exponentiation to it, the compact arc of the exponential function. The idea that you should add that on your own minimal structure, and you get some weird global change, right? Suddenly you get irrational power functions or even exponentiation. As I said, I don't even have any imaginary candidates for how this could happen.
I'm sorry to interrupt. I think, yeah, sorry, it's Vincent. On the Zoom session, we don't hear anything. The mic has stopped working for a while now, for a minute.
We cannot hear you, Chris. No, nothing.
Where's this thing go? This? That?
Much better.
Okay. I don't think I can repeat everything. But okay, but we're going to talk about compact trajectories and path enclosure and the idea that, I mean, there is a loose idea that you can, in control theory or ODE theory in general, but the idea that so compact trajectories should not be sources of trouble. No, to have the information about a compact trajectory is really the only thing this is telling you is that you know how one particular point gets steered to another particular point by some vector field. That this should not have startling global consequences. So in general, compact trajectories should not be sources of trouble, but this is just one of these intuitions or heuristics that people like to use. Personally, I'd like to make this a little more precise, but we do run into these problems that there may be very, very strange minimal structures that we don't know about, where all kinds of crazy stuff can happen. I think just to remind ourselves, we do know that there are minimal structures that have strange properties, and they're constructed specifically to have bad properties by using sort of like infinite pasting constructions and so on. So we know that C infinity cell decomposition does not always hold in minimal structures. It holds in any reasonable ones we know of, but you can actually you can paste together. Well, okay, I'll make it. Imagine this isn't exactly what gets done, but imagine just taking tailored polynomials and gluing them together at the endpoints in crazy ways, any way you want, to wind up making things that are, you're eventually CP for any fixed P, but you have to keep getting bigger and bigger and bigger to get that way. So these have been, these things do exist. So, all right, so now one of the things I mentioned is that, so all compact vectors of linear vector fields are definable from just restricted X but restricted sign. And this comes out of the fundamental theorem for linear systems. Now, so this fact that we're using, that we know we can add all compact trajectories of linear vector fields at any number of variables, does boil down to knowing it about something about planar trajectories. Okay, well, so why is this true though? So the fact that I want to talk about is try to give some reasons why this is true. The fact is that if I have R is a minimal, and so is expansion by all compact trajectories definable planar vector fields. And by the way, I guess at this point, let me just say, all right, well, we'll say that the vector fields are C1 now, if that is needed. Usually the only thing, the most you ever use is local shits, but that's not always true. So if we're talking about definable vector fields now, we'll say they're C1. Okay, so, yes.
Yes, sorry, isn't this linear planar vector fields? Or you said by all compact trajectories of any just definable.
Linear.
Yeah. So this fact. Why is this true? Certainly, so in fact, that this reduces to knowing about all the compact.
You didn't write linear. You meant in the last line.
But no, but I don't want to
Ah,
write.
you don't want to write.
No, this is the point. This is a stronger statement. Okay?
Stronger statement. Thank you.
So this certainly implies this one, and then that certainly implies that for all the linear ones. Okay, so this actually, you can always add all compact trajectories of any definable, reasonably definable vector fields. Okay, and the reason, and so this actually this demands a big black box to do this, and I'm just going to try to give some idea of how this works, what the limitations are, and well, again, since we certainly don't, the open question still remains, of course. I mean, since we don't know when we add this guy, if the field of exponents is preserved, it's still an open question here. We sure don't know, but we do know if we start with polynomially bounded, then we get exponentially bounded after expanding, but that seems very, very, that's very unsatisfying. That is not a satisfiable answer when you're expanding something like compact trajectory. You really don't expect much to happen at all. So we have some glaring holes here. So, and now, despite that we have that, same true even for three variable vector fields, for spatial ones. Spatial definable vector fields. So even though we certainly would like to expect that if you have a decent ornamental structure, you should be able to add all compact trajectories of all definable vector fields, and you shouldn't have anything really change. We don't know. We don't know, and the technology that works here fails here. At least, yes, the technology that gives us this will not work here. And I'll try to explain a little of that as well. Now, of course, there's still these special cases where we should think about, okay, why be motivated at all by this? But let's just recall a special case. So for our special friend R sub n, all right, no, so R sub n certainly defines compact trajectories of analytic vector fields. Not even assumed to be definable, period. I mean, just the compact trajectories are well, they're certainly globally subanalytic sets. They're even analytic sets. So because trajectories of analytic vector fields are analytic, so you go to a compact one, and that's already here anyway. But that's their big. That's by definition, but for special reasons, right? So here's an example, at least, where we know that we can start with it. We can expand at least by all the compact trajectories of some reasonably interesting definable vector fields. And everything stays the same. We have field of exponents Q, and no trouble arises by adding these guys. But this is for very special reasons. Right? So there's just something to keep in the back of our minds while we're considering these questions. So, I mean, ultimately, to me, it seems reasonable when playing the game, if we really ever wanted to, we should say we're really going to insist that we only deal with elemental structures that define or that have field of exponents Q, and don't get upset by expansions by compact trajectories. We sure don't have any counterexamples. So it might, so if you wanted to, you could, this seems like a reasonable assumption to add on as a way of saying, ruling out crazy ominal structures that we don't even know whether they exist or not. I'm not going to do that. I'm simply saying that this is my way of sort of trying to justify this sort of heuristic point of view that, having the information carried by a compact trajectory of a vector field is not much. That's some very local knowledge. It's very limited. It shouldn't actually really cause any trouble with large scale behavior. I agree that that's a good heuristic, but I can't back it up. All right. So now, where does this come from? It comes from a sort of a special case of this big, rather big hammer, Bathy enclosure. I'm not going to give the whole definition here because it takes a while. Also, I should want to give an advertisement again for the lecture notes from the 2009 program. There's a whole chapter in the book on Bathy enclosure. These were notes of the course given by Patrick Schweiziger. So there's all the details you might want are living in there. But so all we only need a small piece of this, actually a little tweak on a special case of this. So this is a big result, a big theorem, we'll say. We need a small piece. And we're going to black box it. Okay. So during today's talk, I'll be. It's too much trouble to try to make global assumptions on everything in sight. So sometimes I'll state things, they seem to not be as general as they ought to be, but it's just because I don't always want to be declaring A's and B's and things like that. So let me just put it this way. So we'll have, so let's start out this way. So let G R squared to R just be a function. Okay, well, we'll say be such that G is minimal. Let's I and R be an interval. Say, could have let it be R all over, I guess. I and R an open interval. F to differentiable such that we have F prime is equal to G of solution to this ODE. So this would be, I mean, F prime T is G of TF of T for all T in the domain. Right. So if you have this set up, then I can add that here is also. So this is the small black box piece. This is all we really need for what we're going to do today. Now, this is actually not very convenient. This is the bare bones result. It's not very convenient to work with in this case because of course, once I do this, I could then do it again. I could say, oh, okay, well, the same thing will be true in here for other things, and the same thing there. So this Bathy enclosure thing is an iterative structure where we start off with a fixed minimal structure, and you start expanding by certain special kinds of codimension 1 surfaces in arbitrary Rn spaces. You do that once, and then you do it again, and then you do it again, and you keep going until you get a limit structure where you get a no minimal structure that's closed under these kinds of special things. So in particular in here, we can iterate this process to wind up with a no minimal structure. If we start with a no minimal structure, we can always expand it to get it to the point where we're basically closed under this kind of operation. Right, so anytime we have a two variable function that's definable and we can solve this kind of ODE, then the solution already lives there. And so we're going to make this convention. So today we'll work with O minimal R that is closed under this process. By the way, a special case of this that's explicitly stated in the early work on graph enclosures is that the case where basically where the x isn't really there. So for example, you can always close under any derivatives of continuous functions of one variable. Just integrate, but this is a little bit more. You have to do a little bit of tweaking to get this variation. Well, we're just going to use it. Just going to use it. Now, of course, this certainly shoots down. This basically shoots down the assumptions I was making the other day about having field of exponents q, because we're going to wind up with e to the x very early on in this game, but that's okay. What we're going to talk about today does not need the special tameness assumptions that I was talking about before. So we're just going to assume that we have a no minimal structure, expansion of the field of reals, where anytime you have an ODE of this form, then it's already living there in the structure. Okay, so this is the black box. Now, Patrick and I were talking about this last night. Yeah, I think it is something that's reasonably important to point out is that this is a very special case of that enclosure, but it's not any easier to prove on its own. You still can't prove this without, you can't get the open-anality without doing the whole machinery. So I'm not trying to pretend like this is an easy version of that enclosure. That's not it. It's just a part. It's easier to state than the whole thing, and this is all we're going to need. All right. Okay. So this is what we're after. After sort of a sketch of a proof of this. I just won't go too far down. Okay, so now let's start drawing some pictures and getting some data here we can work with. So some notation and things. So this will be, so plain our map here. I'm going to say it's going to be definable in my own minimal structure. Let's make it C1 just to avoid annoyances. And the only zero, it has 0 at the origin, and that's it. Now, does it need to, of course, it doesn't need to be defined everywhere. What I'm going to be talking about really is all about being in a neighborhood of the origin, more or less, or whatever, but this is fine. So this way I don't have to like keep saying let X be in here and blah, blah, blah. So this will be, you just fidget the notation when needed. So gamma is going to be a non-trivial trajectory. So that means it's not a point. And so because of our assumptions here, so it doesn't touch the origin. I should say doesn't include 0. So it doesn't include 0. So disjoint from 0. Then in the C1 case, if you have a trajectory that has 0 in it, then that's it. That's the end. You can only be. And we have to get another line here. Let's let P be a point in gamma.
The middle F should be capital F, I guess. So you write F in the.
Yes. All right, I'll leave that. That's all visible, I hope. So then the claim here is that there is a neighborhood of P. I guess I should give it a name. Of neighborhood P, such that U intersected with gamma is definable. So this is the general thing we're going to try to prove using the black box. Now, this immediately gives us the fact, because if my trajectory is compact, you do this around every point, then only finitely many of the neighborhoods is necessary, and so my compact trajectory is definable. So the game here is that we really want to show that in this setting that if you have a trajectory, then locally at least it's definable. And remember, I'm assuming this because otherwise I just have to keep saying there's a neighborhood in which I could add that to my original minimal structure and it's still be definable. And that gets a little bit annoying to have to keep saying that too long. So that's the only reason really that I'm using this assumption is purely for convenience.
Chris, is it true that when you say compact trajectory, you actually get more, you get actually a compact piece of a trajectory? So the end point, you don't care what happens. So you don't have to close back to themselves to be C1 everywhere, right?
By compact trajectory, I'm in this case with the other assumptions that we're making here, this is basically the same thing as saying that, well, that you're also going to be the image of a compact, you're going to be the image of a solution on a compact interval.
Right, but the end, what I'm saying is that you don't need the compact trajectory to close back to itself to be smooth everywhere.
No.
Right.
No.
Okay.
No.
So it's not, yeah.
Okay. No, we're just talking about pieces.
Right.
Pieces. Okay. All right. So basically, so this is really what we need. We need to prove is that trajectories, non-trivial trajectories, like definable C1 vector fields, in this case, are locally definable. Okay, that's basically what we're going to do, and in order to do that, we're going to show that locally we can reduce the trajectory, we can reparameterize it, so that we're going to be satisfying a system of this sort, either going to be satisfying it this way or this way. Really, I mean, it doesn't. We might be looking at things sideways, but this is the game. So how does this maybe work? So this is just a sketch. Some details that people should learn. So we know one thing. We know either F1, the first coordinate, F1P is not equal to 0, or the second coordinate P is not 0. Because if they were both 0, well, we're not including the origin. So we have no zeros. The only zeros are at the origin. So we have this. So let's say the format. Why not? Okay. Why not? Okay, fine. Now, and then of course from here, you can also then say, we know that either F1 of P greater than 0, or P must be less than 0. Nice, easy case distinction. And again, we'll say the formula. All right. So this, of course, means that this condition, a little bit softer. So F1 is always positive near enough to P. So we're going to be using this now. Okay, so let's see. So we need some other things here. Let's say, so near P. Now, remember, my definition of trajectory is pretty naive, right? You just have to be the image of a solution, and that's all you have to be. So near P, we have that gamma is equal to gamma is the image for some interval and a solution. So that, so basically I'm just going to shrink. We know in the end, we just want a local result. So I'll shrink I if I have to, and I'm just going to say that this is what I look like. Gamma is this guy near P. Okay, let's see, do I need it? All right, just in case. There's some T naught, so it's a gamma of T naught. I'm not sure I actually need that, but I might. All right, so here we are. We are, the first coordinate is always positive near P, so we'll might as well take that to always be true here. So now what does this tell me? This says, so gamma 1 prime has to equal F1 of gamma, which is always going to be greater than 0. So my solution here, actually we're going to get a little, my actual solution here, gamma 1 is, strictly increasing. Has a compositional inverse. It's 1 on the appropriate interval. Okay, so now here's the. I don't need that anymore. So now we get to do a little calculus, very easy. Well, so I think I really could have just drawn pictures for all of this, but of course pictures aren't proofs. So we have to do a little bit of actually verifying things. Okay, so now what I'm looking for at the moment is basically I'm looking to make sure that I'm trying to get that near my point P, I'm actually living on one of these solutions, is that I can transform so that I look like I've got something like this. So we need a G, and so here's what we're going to do. Where F1, Xy is not 0, and then we'll just make it 0 otherwise, because just so that it's totally defined. Now remember, over here, I had no assumptions whatsoever on the G except definability. No assumptions on G except that it's definable. Okay, well, I leave it to as an exercise to check that gamma 2 composed of gamma 1 minus 1 prime is going to be equal to T gamma 2 composed of gamma 1 minus 1 on an appropriate interval. Gamma 1 of I guess it is. Okay. Now, all I've really done is reparameterize. All I've really done here is reparameterize what the trajectory looks like near P. Okay, that's all we've done here. So, or basically, so by the black box, gamma 2 composed with gamma 1 minus 1, going from gamma 1 of I. I guess I can still, that's the same I guess. Yes, is definable. But what is that? So it's gamma I, which was what our trajectory was in the first place. And that's what we wanted. Okay, so this is the calculus proof where you don't actually use any pictures. Now, in the original definition of Faffian and all this, what we're really talking about is like this row, leaf, and plane or something, right? I mean, this really boils down to the fact that Rolle's theorem or the Cauchy value theorem or whatever you want to say, this holds in the plane. So we know that the trajectory, well, it has to be doing some kind of stuff. And if you start, drawing and looking, well, okay, there's some places where it's going to be the graph of the function. There's going to be some places where maybe it looks more like that. And so it's the graph of the function in this direction. But in any case, this computation shows concretely how we can use the black box to get this local condition, which then tells us that the compact trajectories are definable. I'll leave it to you to draw the pictures if you like. They're very instructive as well, and there might even be pictures in the literature that I've alluded to already. Now, seems pretty easy. Why do we not know what happens in free space? The technical answer to that is that a trajectory in free space is codimension 2. And though there have been many attempts over the years, some people around here might have known of some of them. There have been many attempts over the years to kind of do this, to try to develop this Faffian stuff over codimension 2 surfaces, and yeah, it just doesn't really. These have all failed so far. So this Faffian, it's ultimately based on ideas of Polanski, and these really pretty much require hypersurfaces, codimension 1 surfaces is where this stuff works. The technology breaks down when you go to higher codimension. And we would love to figure out ways to make it work, but so far, no dice. So at the moment, this is the sort of state of the art as far as saying, that I can that I really don't have to. That compact trajectories for the definable vector fields, they don't actually carry all that much interesting information on their own. They shouldn't actually make for big global changes. And so this sort of squares with points of view. So I like that. All right, so what are we going to do with this now, though? Some questions? There's a class I should ask once in a while. Okay. Oh, so I have an anecdote to relate while I'm getting ready to. So for any students or younger folks in the audience, I'll tell you a little story behind this talk today. So I was trying to think about what I was going to talk about today, and I started thinking about this, and I thought, that's too easy, and that's ancient history. You know, I wrote this up, I didn't even know when we wrote this up. You know, so this is too easy, and maybe I should think about doing something else. But I thought, well, okay, I'll go look at my old write-up of this, and maybe see if I should do it anyway. Well, needless to say, I got completely stuck in two different places where I read something and I said, why is that true? And it actually took me quite a while to figure out why this obvious thing that I put in these notes was true. So the moral lesson of this is that sometimes it's easy when you're working on things, when you're in the midst of it, you can actually start to trivialize things a little too much. And you begin to think, oh, well, that's easy. Yeah, wait till 10 years after you write it and recheck it. So I would argue for your old age that you make sure the details are there.
You always write short.
Huh?
You always write short, Chris. You have very short papers.
One
And
has
we all
to-
have to work very hard to unravel.
No. It's, you know,
Really true?
a clean station is a happy station, okay? Your station should be well organized and efficient. But I overdid it on my notes, so I don't know, I thought this was a good lesson for people. It is possible to do this. So now what I'm just going to give is a brief glimpse at what I'm going to what's coming next and what we'll start in on Friday. Right. Okay. So this is this thing that I borrowed some language from a book by Arnold. Who gave talks at these very boards. And I was here. So what we're going to call this is the fundamental alternative. Now, this is a result that's really about analytic vector fields in the plane. It's been around for a long time. And it's very easy to explain by picture, but then putting this all together and making it precise it does take a little more work. And we're going to be doing it in abstract minimal structures. So even there, we need to do a little bit of work here. So the setup is essentially the same. We've got a vector field, a definable vector field. We can go ahead and say C1. We have an isolated singularity at the origin. So there's 0 here and no other zeros nearby. Now this fundamental alternative says that there's only 2 possible behaviors if you have an analytic, not C1, analytic vector field under these circumstances. That either you have what's called a characteristic trajectory. It's something that comes in to the origin. Well, sorry, if it has any, careful, yes. We have to assume there's at least one trajectory that does come into the origin. It could be a center, it could just be circles, that kind of thing. Or we're not looking at those. We're looking at the case that we actually do have a trajectory that comes into the origin. So in that case, you have to have something that has a well-defined tangent as you come in. So there has to be a curve like this that comes in, and there's a well-defined limiting tangent when you come in. And so what this means is because trajectories can't intersect themselves, at least not in locally Lifshitz vector fields, this means that basically any other trajectories you have that go to the origin have to stay away from this guy. So you get maybe some kind of picture like this. Other things can happen. And then what happens is there's only finitely many of these things that show up, and the directions, the tangent directions, can usually be figured out from the linear part if you have that. And you get these, what's basically an O-minimal picture, right? You'll have, so all of your trajectories will wind up coming in, and any finite, all the collection of all of them together can be added. They're all jointly O-minimal. In
But
fact,
what do you mean only finitely many? What finitely many?
Basically, what I mean is these characteristic directions. There's finitely many, and then all the, so like you can have families of things that are,
Or,
the phase portrait is doing like this. Saddles. I don't want to get into the whole
all right.
classification thing. I'll try to be more careful. So you either have this, so you have one trajectory that comes rocketing in here or away from it, but I don't care about that either. I'm talking about the set, not whether it's coming or going out. And the other and if that doesn't happen, then you have to have some kind of spiral of something or other going on here. Some kind of spiral. So it's either this or it's this. This picture turns out to be an O-minimal picture. This picture obviously does not. And so these are the only two possibilities that can happen when you have an analytic vector field. And basically, this is also true for arbitrary O-minimal structures just under the assumption of C1. I'm not even sure probably locally Lifshitz is enough, but again, C1 is convenient. Okay, so this gives us another reason to be interested in spirals. When we have this thing, if we're looking nearby, we're either going to be in a setup because of what we just did. In fact, we'll be able to prove that not just the compact trajectories, but all of these things together will live in my O-minimal structure, in a fat enclosed O-minimal structure, or we're going to actually have a spiraling object that has well-defined intersection with transversals and a return map and some things that show up in classical. You might say, well, that's not very impressive. What else could possibly happen? I have just a couple minutes, so let me go ahead and show you. What else might happen? Well, no, actually, we've assumed that at least one trajectory comes into the origin. So yeah, there are, however, if you allow C infinity but infinitely flat at the origin vector fields, you can actually come up with things where these don't work anymore. There are other strange kind of things that can happen. That's another reason not to look at trying to solve arbitrary, trying to deal with trajectories over exponential O-minimal structures, because you can come up with some, once you have infinitely flat trajectories at a singular point, it's very, very hard to tell what's going on there. So this should still be true. All right, I have to think about what I just said here. Anyway, these are the only two pictures. This has been well known. It's if you want to see a complete proof that's sort of classical for the analytic case, again, that would be in Fernando Sanz's notes in 2009, Sanz chapter in 2009 lecture notes. Lots of nice material in there, by the way, and pictures that are much better than I can draw. But I'm going to actually, we're going to reproof this just in the O minimal case and show that the same general qualitative behavior holds, although we'll have far less. We won't have good information necessarily about like what are these actual directions that show up. We'll just know that that we have things like this. I think it's time for me to stop. Any questions on anything? Right. Well then, so on.
Is it possible to say in a few words what these characteristics, how do you call them, characteristic trajectories? or
Characteristic directions are.
Directions are, and what makes
Well,
it characteristic?
Basically, I think what you do is you switch to polar coordinates and then look at your power series expansion there. You could start looking at where the zeros are of your leading polynomial on the circle, or in homogeneous coordinates.
Ah, okay.
And so then you could see, I think it has something to do with the locations of the zeros there.
Oh, okay, I see.
All right. So, but there you really have the information from the Taylor expansion of what and you have these homogeneous polynomial expansion, and I'm pretty sure you get the characteristic directions from there, if I remember right. And we won't have that. We won't really have that in general in this setting. All right. Good. We'll see you Friday. I hope.